Hey everyone, my name is Michael Gleiber and I'm with Bosch Corporate Research in Renningen, Germany. I will tell you something about end-to-end performance assessment with TVM and virtual models today. The use case that I will show you in this presentation is object type classification of radar spectrum data that we will deploy on a virtual target hardware. To do so, we first had to bridge the gap between the tensor intermediate representation and the deployment of an abstract task graph on a virtual target hardware. Therefore, we built a tier graph parser. After this, I will show you the whole new possibility this opens in terms of virtual performance analysis and in terms of design space exploration, as well as on the software level as on the hardware level. At first, let me give you some insights. We have an automotive radar neural network that we want to deploy on an in-house CGRA-like embedded accelerator device. So this accelerator device is highly configurable. It means we have so many parameters before we really produce it that it's really hard to explore. And therefore, it's also not possible to build a toolchain for all possibilities in this stage space. Therefore, we built a TVM backend that we can hook up with virtual model simulation tools. The goal here is we can tweak the state space of the hardware device, for example, changing the number of processing elements, changing the bus width, or changing the internal memory sizes. And therefore, it's possible to give a performance estimation prior to RTL implementation and prior to building an entire toolchain. From a methodology point of view, the really big difference is instead of building a binary for a target hardware or for simulation or on an RTL tool, we build a task graph that we simulate on virtual hardware. What is a task graph? A task graph is what compiler folks might call a function call graph, plus we additionally add timing information to it. This nice picture here on the right shows a radar spectrum containing a stop sign and a motorbike. So you can have further information besides, oh, there are two objects in my way. So using object type classification, you can answer questions like, is the object overridable, or tell the difference between a person and a soda can. This is a highly relevant question to extend capabilities of other assistant systems, for example, by providing a region of interest. For example, to tell the vision system, have a closer look at this region, which is highly relevant in difficult situations like difficult lighting conditions or difficult weather conditions. You might now say, this looks like a solved problem because we know how this is done in vision. But for radar, unlike in computer vision, applying deep learning is really in an early stage. And our colleagues from BCAI and University of Stuttgart have done a really great job in creating the neural network shown here below, which can tell the difference in the radar spectrum, for example, between a baby carriage and a garbage container, which is a highly relevant question for decision making. In order to execute this neural network efficiently in an automotive context, it is really crucial to have an efficient embedded accelerator. The one I'm showing you here is a CGRA-like accelerator built by our Bosch colleagues. It consists of multiple base blocks which are connected. So some of these base blocks are load and store blocks that have nested hardware loops which are configurable. Then there are other blocks that carry out arithmetic and logic operations such as multiply and accumulate, ReLU, or the exponential function. And all of them can be connected to a multi-bank internal scratchpad or to an external interface. From the point of view of a design space exploration, it is important in the software domain to solve the scheduling problem, which I can show you today. And from a hardware perspective, it is interesting or important to find out how many such hardware loops do we actually need. How many internal memory do we require to meet a certain performance requirement? When I first tried to manually create a schedule for such a device, it ended up to be very, very similar to TIR code, that one of my colleagues has shown me the week before. And that's how the journey began, that I can show you this presentation today. The first challenge was connecting TVM with our abstract virtual simulation environment. For example, bringing a TE statement like the Conf2D shown here into a form that it can be really simulated on an abstract hardware model. And if you look at the TIR representation of the schedule, you can see there is actually everything that we need. We have all the important values of the counters inside the for loops. We have assignment operators, we have arithmetic operators that can be mapped to ALU blocks. There are array accesses which can be mapped to load and store blocks. So you can see we have everything we need to build a target-specific task graph. So let's have a closer look into the semantics of such a target-specific task graph. Each colored node here is mapped to a hardware resource. For example, the cyan one is mapped to a load block and loads input features. The green one is mapped to a load block and loads weights for the convolution. The red one is mapped to an ALU block and carries out multiply and accumulate operations with the data that are fed by the load blocks. And the outputs of the multiply and accumulate block are fed into the store block, which is here shown in orange, which stores the data into the memory again. You can see that each of the load and store blocks has a number of hardware counters denoted as x0 through x3, but there are also more possible. And these are used to generate addresses that are loaded from memory or in the store block, which are stored to the memory. So every time an address from the cyan and from the green block is generated, data word from the internal or external memory is loaded. The result is forwarded to the red block, which is the MAC block. The MAC block accumulates the received data for a given number of values, here for example 800 values, and provides after 800 accumulated and multiplied values the result to the orange block, which then stores it to address. And address where this data is stored to is calculated also from the internal hardware counters. The second information embedded into the task graph is the data path of the hardware. So this path must be configured prior to execution of the task graph statically. So a specific load block is connected to a specific MAC unit, which is connected to a specific ALU, and this is connected to a specific store block. So data that is loaded by a load block, for example here the cyan one, is loaded from the internal memory, forwarded to the MAC block, accumulated, and then forwarded to the ALU block, where for example a ReLU operation is carried out, and then the result is brought to a store unit, which then stores it again into internal or external memory. In order to perform the Conf2D operation that we have described as tensor expression before, it is crucial to use the correct counter values for the individual blocks. So for example, the counters that we have found for the array access operations have now to be mapped onto the load blocks. That's it. We now have a functionally correct implementation of Conf2D on our target hardware. But it probably is awfully slow. But I haven't given you the full picture of our hardware yet. So the hardware doesn't consist of only 2 or 3 such blocks, but it's a configurable number of hardware. So we can have n of those working in parallel. And this is where the cool scheduling features of TVM actually come in handy. By unrolling one or multiple axes onto the hardware devices, it's now possible to parallelize the whole Conf2D operation and therefore parallelize and accelerate the whole operation. In many cases, the result schedule has more loops than we actually have available in the load and store blocks as hardware loops. In this case, it is required to transform them into software loops, which are orchestrated by a host device, for example by a processor. For the task graph, this means every time the hardware loops are fully executed, we have to add additional nodes shown here in white. These are nodes orchestrated by the processor, which actually reset the base address of the hardware loops and let them run all over again. Okay, now we have an optimized schedule. How do we come to realistic performance evaluation now? Well, at first it is necessary to have a virtual hardware model, and you can see a block diagram of it below. So it is necessary to model all the connections of the resources and the possible conflicts. So for example, if two load blocks simultaneously access the same SRAM bank, there's a conflict, so one has to wait. And this is exactly what you can see here in this Gantt diagram. So the upper one gets full access all the time, and the lower one has these interruptions in between. So we go from annotated latency to really simulated latency that represents the actual functionality of the hardware. The same thing holds true for dependencies. So a load block that is delayed cannot trigger a MAC block, and a MAC block that is delayed cannot trigger a store. So these one have to be delayed as well. So our simulated execution is based on simulated latency and the dependency that is given in the graph. This might seem easy with this simple example, and some people might even say, I can do this with a spreadsheet. But think of millions of transactions that you have to keep track with, and hundreds of dependencies. Well, then you need really a serious simulation environment. And this is what I can show you here. So this is a screenshot of the simulation that we use with a number of parallel load blocks, store blocks, and MAC blocks to simulate each transaction between each of the blocks for the entire OTC radar network that I have shown you in the beginning. And when seeing this, the advantages are probably pretty clear. When doing performance evaluation on such a virtual model, it is possible prior to RTL implementation to give really accurate estimations about latency. So how long does my neural network take to be executed on a specific configuration of the embedded accelerator? Are there any congestion effects? And how much memory bandwidth is required? With regard to software, it is not necessary to implement a full compiler backend. So we can evaluate mapping strategies or tiling strategies here on the virtual model and implement only those for the backend that we found to be successful and which are efficient. Looking into the future, we can also think of using auto-tuning, and this can benefit from detecting internal SRAM collisions or different pipeline matchings. And this possibility to analyze and to explore in a very early stage of the problem actually opens up the entire design space for us, because doing a bottleneck analysis, a bandwidth analysis, and a latency analysis in such an early stage of a project brings whole new possibilities. So imagine there's one layer in the neural network that really performs bad. So you have three possibilities to improve. You can ask your algorithm guys to execute other neural network structures such as different kernel sizes and so on the virtual models and check if the performance improves. The same model can also be used with the algorithm provided by the AI guys, by the compiler guys, and they can simultaneously check new scheduling algorithms or mapping strategies. If both fails, the hardware people can still change the parameters of the bus to increase the bandwidth or add more memory. And then the whole development loop can go over again. To summarize my talk, for workload generation, we use the TIR abstract syntax tree to generate a task graph. In our opinion, this has auto-tuning potential. And this task graph is then deployed on an abstract hardware model. We simulate this task graph on an abstract hardware model instead of simulating a binary on an RTL level model. In a system context, it is possible to evaluate shared resources, detect contentions, detect race conditions, and also do a bandwidth optimization with other components in the system. Last but not least, which is for me one of the most important things actually, is that this methodology makes it possible for cross-domain decision making. So such an early performance prediction by simulating relevant parameters allows, for example, that AI developers can use the model to determine the impact of their changes on the hardware. And this hardware is not even built yet. So this is pretty cool. What this eventually means is that in such an end-to-end methodology, the model influences the realization of the hardware, of the algorithm, and of the software. So that's the end of my talk. Thank you for your attention.